Yes. So the PVNRT, it's a very important um, equation, and you will be using it on and on and on, even for future calculations. So when it comes to the gas stoichiometry here, you have to use PV equal nRT. And all those PV nRT is the most important thing is N. N is the number of moles. Then you have, Avogadro says, 1 mole of any gas will deliver us 22.4 liters. So an STP means I have the pressure is 1 atm, the volume is 22.4, and the temperature is 0 degrees or 273 degrees. So you have the initial volume, whatever the gas is. We'll see some of the examples when we go through this here. Some examples are there, so you can see those here. Some of the examples are there. So the gas stoichiometry is nothing new. You do it the same thing with the mole ratio that we did before. Just here you have to watch, because we are dealing with the gases. You have to use PV equal nRT, and then you use the STP conditions. STP condition, the pressure is 1 atm, temperature is 0 degrees or 273 Kelvin, correct? And the 1 mole will deliver for you 22.4 liters. So you have two conditions. This is like initial one, and then you have to look at the volume or pressure or whatever is a final condition. So the next here, so I want you to make a note of this. You need the formula of the gases. You need to add to this gas law, ideal gas, and you need to know the gas constant. It has two. I mean, it has more than this, different units, even English system units. But we are even SI units. But we are using the mostly used in chemistry and physics are 8.314. That's when when you calculate. That's when it comes calculate for the energy or heat in joules. That's whenever it's joules there, you use this. This one here is just normal one, mostly heavy used than anything else. 0.0821 liter atmospheric pressure per Kelvin per mole. So, as I said, you need this equation. You put it aside with the R gas constant. So when it comes to calculation, you know how to use it. Now, molar mass. Well, we said the mole is the ratio between mass and molar mass, correct? Mass and molar mass. So the let me write it here for you, just you remember that, right? So we said mole is defined as a ratio between mass over molar mass. It's always the case, correct? Now cross multiply. So molar mass will be mass over what? Over mole. So if we know the mole by definition is the ratio between mass and molar mass, so the molar mass will be mass over number of moles. So now this we can determine this one for the gases from the ideal gas equation. So we can determine this from the ideal gas equation. So let's go for the density. Let's go for density. You go for the extra credit. Go and write your name and come back, please. It's no penalty. Just go and write your name, get yourself 10 points. Yeah, I will tell everyone is coming. So density, what is the density? Density is a ratio. The same thing, moles are ratio between mass, molar mass. Density is a ratio between mass and what? Volume. Anytime I have a mass over a volume, I deal with the density. It's a ratio, nothing else. It's a ratio between mass over volume. So that's the density here. So now with this one here, don't worry about the molar mass. The molar mass, because don't worry about the molar. The molar volume means you are working with STP for 1 mole. So density for 1 mole gas, right? So for 1 mole gas, don't worry about the molar. But the real density definition is mass over the volume. When you are relating to 1 mole, then yes, then you say molar mass because you are relating the density to 1 mole of the material itself or a compound, correct, or matter itself. So anytime I have a ratio, mass over volume, this is the density. That's another ratio. And you will see in physics and chemistry and engineering, most of the formulas or laws, you will see that's physical properties are ratios, density, correct? What else we have seen? Molar mass, and then even go for freezing point. All those are ratios, whatever actual temperature to atmospheric condition. You look at the atmospheric conditions, which is this temperature is recorded at 1 atm. Always ratios with you, refractive index. So here it is. This another example here. Gas density. So, well, this is from the formula here. Look at the formula. This is very important. You have to put it there. And when you put this one there, you divide both sides by what? By V. This one by V, this one by V. By doing this, so the V cancels out, correct? So you have P equal N over V RT. So don't worry about RT, that's there, but NV, that will give you the density. What is N? Is number of moles. Well, N is mass, correct? Over N is molar mass. Here it is, molar mass. So mass over the molar mass, that's the N. And the whole thing here divided by V, correct? Multiplied by RT. Correct, guys? So now look at this. You can put molar mass at the bottom, correct? You can put molar mass at the bottom and then RT. So you have here, look at this. So I can look at this formula here, pull molar mass at the bottom. So I have, and pull RT at the bottom. So I have P equal over RT. I put RT at the bottom, correct? So equal to mass over volume multiplied by 1 over molar mass, right? Sorry, here, molar mass. So mass over the volume, what is mass over the volume? This is the density, correct? So P divided by RT, equal density over molar mass. right? So you can see how we transferred everything here. So density over molar mass. So with this one here in mind, the same thing here. Look at this formula. You have to keep this formula in mind and put it aside. So you know the density is the pressure multiplied by the molar mass. This is molar mass here. This is M, molar mass, divided by RT. So this is the density here. So can you play it around? Yes, you can play around. You can, if the density is known, you can write the molar mass. The molar mass is density over RT divided by P, pressure. So this is how to get the molar mass. This is molar mass. See it here? So this is another law. Just write it, please, in a piece of paper. Will help you to visualize how to calculate for this. So let's do this. Now, next one here, we are looking at partial pressure. What is partial pressure? Partial pressure, when the gas is in a mixture, this gas will act upon itself and upon the wall of the container, putting pressure on the container surface walls. And this is we call partial pressure. So it is by itself. Each gas of the mixture here will have unique pressure on the surface wall of the container. So this one will be exerted by each gas in a mixture. So if we have a mixture here, so you can see here, each one those by themselves. We have them together here. We mix them together. This is the mixture here. Each gas of this one here, see different pressures here. And this is partial pressure, part of the total. Partial pressure means part of the total, part of the total pressure. Each one will contribute to the overall total pressure. So this one comes 300 kilopascal, 600, that's 900, 450, and the total is 1,350, the sum of all partial part of the total, the sum of all the partial pressures is 1,350 kilopascal. So that's what you mean by partial pressure. So, and this code here, and you write this one here. This one here called here, this is Dalton's law. Dalton's law tells you the total pressure of a gas mixture is equal to the sum of all partial pressures in the mixture. And that's what we have seen an example here. You look at this, that's the example here. This is the total, the pressure on this container mixed with the three different gases is the total of the pressure of each one exerting on the wall of the container itself. Correct? So, like fire extinguisher, you put two ATM. Correct? Carbon dioxide is sublimes, cannot be solid. Correct? Sofian, did you go to the extra credit? Okay, like last time, correct? Okay, I know you will go there. Okay, so here it is. Fire extinguisher has two ATM, 2 atmospheric pressure. The carbon dioxide is a gas. When you press it too much, 2 atmospheric pressure or more, you make out of this white powder. So the white powder coming out of the fire extinguisher is nothing else than carbon dioxide gas, compressed, correct? As soon as you put it on the fire, this white powder will disappear. It's a gas, CO2 gas, but compressed. So now, if you have like this 2 ATM, and then other fire extinguisher has about maybe 10 ATM, and you mix them together, So the sum will be 2 plus 10 will be 12 atm. Are you following me here? So the total pressure of each container, pressure N, will be the sum of all the partial pressure of each container here. And that's what we have here. And that's what we call Dalton's law. Dalton's law tell you total pressure is the sum of a mixture of gases. This is always a mixture. The key is a mixture. This is not true if you have anything. The key is, this is the keyword of the mixture. So if you have a mixture, you have this partial pressure, the sum of all the partial pressure. This is Dalton's law. So write it down. Write it down so at least you can. Now, mole fraction, the mole fraction is a fraction of a mole. You can't tell. What is mole fraction? Mole fraction is fraction of a mole. Now, if I have a fraction of a mole, if I have a gas, so if I have a gas A, this is gas, correct? When I say mole fraction, what it tells, what it will be? Fraction of the mole will be what? Fraction. Mole fraction is a fraction of a mole. So fraction of a mole. So this one will tell you N, the moles of N gas to N total, correct? That's a ratio. Mole fraction is a ratio between the mole of the specific gas in consideration divided by the total of the gases in a mixture. So that's the mole of the fraction of the mole. Means you have one gas, divided by the total, you get mole fraction. That's what it says. That's what it really is. So, and if you look at the whole thing, this is the definition of the mole fraction. And then we'll see how it relates itself to the partial pressure and to the total pressure. So here, if you have a mixture, like nitrogen is 78, composition of air, and it's partial, that's find its partial pressure. So what will happen here, this percentage is, put it there and multiply it by 1 atmospheric pressure. You assume that's the air inside. It's 1 atm. So you multiply it, this is 1 atm. So oxygen is 21%. Nitrogen is 78%, by 1 atm. And the rest is 0.01 is whatever gas is inside the air, which is carbon dioxide and halogens, correct? So if you add them up, it will come up to 1 atm. Now let's go back to the definition of mole fraction. Here is the mole fraction. You see it? Makes sense? You have a gas A or B, whatever. So the mole fraction is the mole of that gas divided by the total. It's part of the total, number of moles. So this is the mole fraction. How we get to this conclusion? Well, we applied the gas ideal gas equation or ideal gas law. This is the partial pressure of a gas A divided by its total. So this one will be RT divided by V. RT, that's cancels out because no change. So will be NA divided by N total. This one here is NA by N total, and we can tell this is mole fraction X of A. So we can put this one here. See here. So we can put this one here, and we said, okay, if that's the case, then we can put the formula here and work this formula here. PA is the P total multiplied by the mole fraction. Again, I want you to write this one here. Partial pressure equal to the total pressure multiplied by the mole fraction of that gas in a mixture, correct? And the total mole fractions has to come to be what? To be 1. It cannot exceed 1. It has to come to be 1. So if I have mixture of XA for example, plus XB plus XC. Now the sum will, all the mole fraction will be normalized as to be 1, correct? As to be 1. So let's look at the examples here. Okay, so what will be, maybe I will increase this one here, you can see. So we have, okay, so you can see it much better. So you have 3 gases. We did not mix them yet. Each gas, it has its own bulb here, its own container, glass container, and carbon dioxide, hydrogen, and argon. Each one is existing in its own conditions. So the containers is size is from the carbon dioxide is 1.5 liter, and the pressure on this container is 2.13 atm. This one here, hydrogen, and it has this condition. The volume is 1 liter, the pressure is 0.861. And the argon here, it has this one. It's asked to you, what will be the pressure in the system if we open if you open this, they'll start mixing. What will be the final total pressure of all those? Well, this is a little bit tricky because you will not know how to do the ratio. So, but Boyle's law will tell us we can do it. We can do it. So we'll use PV, see here, PV1, correct? And then from there, we'll add all those PV2 plus PV3. Remember, it's Boyle's law, PV1 equal PV2. 1 is initial and 2 is the final. That's Boyle's law. This is Boyle's law. So we calculate the whole thing. So we calculate everything here. And after the calculations here, so you will add up the whole thing together. So whatever the value here is multiplication of all those here, those 3. This is here. This is here. And this is here. Right, guys? So you can see all those here and you can calculate. After calculating, then you put your condition because you don't know what's the condition are. Well, you look at the volume. What's the total volume here? This is very important to know the total volume. So the total volume, total volume is 2.13, correct? Plus 1.00 plus 2.00. So now we have the product of the Boyle's law for each gas, correct, after mixing, and we know the total volume. So we set up the whole thing here. Look at the answer here. So we set up the whole, this is for the, this is for carbon dioxide, and then you do it for all of them, correct? And then the whole thing is, this is just for carbon dioxide, and you'll do it for all of them. You get the sum of all, correct? Remember BV1 plus BV2 plus BV3 is this one here, is this one. Right? That's the sum of the, when you multiply. Right? This is just for show you how to do it for one of them, CO2, but when you add them up, you come up with 6.3. After you have opened the gas mixture, then the volume will be, the total volume will be 4.5, correct? You add all the volume here. Let me go up and look. It is 1 plus 2, 3. 3 plus 1 is 4.5. So you can see that 4.5 is the total one. So you have here the total, which is, this is your V2, correct? And V1, V2, this one here, you know, the value of it is this, right? So you can calculate the P2. So P2 will be the whole thing here divided by V2 here, total of the volume. This is total of VV1, VV2 plus VV2 and 3. The answer is 141 ATM. So the answer is 1 ATM. So what we have, we just solved for this P2. That's the total one. That's total. And this is the total of, this is total, This is total, sorry. This is total, which is sum of this all stuff here, total of the pressure multiplied by the volume. So now you can get the total, when you mix them, is the pressure is 1.41. We did what? We used Boyle's law. Now, which one will have more number of moles? Well, you just apply this. The PV, you have it there. That's the total here, which is this one here, right? This one here is given to you. Look at this. So PV and RT divided by RT. RT are the same, they don't change. This is the total one here. And this is, you calculate what? Calculate the mole fraction. The mole fraction is Ni, that's for carbon dioxide. And carbon mole fraction of the moles of 3.19, correct? For the 3.19 is coming here from here. 3.19, that's for carbon dioxide, divided by the total, which is 6.36. It came out to be, the mole fraction is 0.501, which is the largest of the gases, because the other gases, as I said, the sum of the whole mole fraction is 1. So if you add the mole fraction of both of the three ones here, let me see here, mole fraction of CO2 plus mole fraction of hydrogen plus mole fraction of argon has to equal to 1. So if the carbon dioxide is 0.501, so carbon dioxide will be the largest, the most abundant inside after the mixing, correct? So this is just take some time to understand, but it's not really difficult to follow. Now I need some help here. We need to solve this problem. I have no solution for it, but together we can get the solution. A gas mixture contains hydrogen, helium, neon, and argon. How many gases? We are dealing with 4. The total pressure, so the total pressure, PT, P tot, total, equal to the partial pressure of hydrogen plus partial pressure of helium plus partial pressure, oops, sorry, plus partial pressure of neon. Right, guys? Plus the partial pressure of argon. So the total here, all of it equal 93.6. Okay, now I have just to replace those. Helium is this. So helium here, hydrogen, I don't know. Oops, sorry about this. So hydrogen, I don't know. Plus for the helium is 15.4. For neon is 25.7 plus 35.6, correct? And the total is 35.6. Can I solve for this? Yes. Can I? So what's the answer will be, you think? What's the answer? You move all those the other side, so it will be this one here, the hydrogen will be 3 point, not 35, sorry. Tell me about here. So this one here, this one here is 93.6. So to add all those up, .6 minus 15.4 minus 25.7 minus 35.6. What's the answer here? Somebody has it? 16.9. 16.9. Can we verify this? Yes, we can. If we add this, those three, correct, it has to give us this total. And it does, correct? 16.9. So this is how you solve this type of problem. So the last topic in this chapter is about the diffusion. Well, if you are taking A and P, somebody is taking A and P biology. There is A and P1 and there's A and P2. So, well, diffusion is the same definition whether you are taking biology or chemistry or physics or engineering. You go always from higher concentration to lower concentration, correct? That's the way that things are diffused. It's always from higher to lower. So higher concentration too. It's, you can imagine, you cannot come from lower to higher because you started lower, you cannot go to higher, correct? Unless you are compressing this gas. So therefore, diffusion in chemistry or in human cells or in biology or engineering, always from higher to lower. Osmosis, from higher to lower. From higher, always remember, from higher. Osmosis, the same thing, it's a pressure, correct? Goes from higher to lower. So the diffusion is a movement of particles from higher to lower concentration, correct? So here it is. See, here is an empty container and the high is here. So when it starts, this starts spreading out, you get something looking like this. Look at this. Before the diffusion, they are there, but after the diffusion, they are spread out. So the molecules are not near each other. So, and I want you to write this formula is very important, called Thomas Graham, or it's known by Graham law, Graham diffusion law. Write it in a small piece of paper for the effusion, for effusion. For example, if you have a tire, your car, and somebody punched this tire with a nail. So, wow, you took the big one? How they give you the big one? Lucky me. So the other ones get the small one? Who get the small one? Okay, somebody got, so that's, you can use it for home, then this, hang it on the wall. Okay, so good luck, good luck. Yeah, so Graham's law tells you that if you have a tire, correct? Now, if you have a tire and you made a small tiny hole inside this tire with the nail. Now, and you have, then air will come in. Air mostly is 78% of nitrogen and about 21% oxygen. About. Which one will go in? Nitrogen or oxygen? What do you think? Grams will tell you this is always indirect proportional square root of their molar mass. So what do you think? There is a small tiny hole and you made a punch inside your tire and the air will come in. The air made of 78% nitrogen and 21% of oxygen, correct? Which one will come first inside the tire, nitrogen or oxygen? What do you think? Somebody will help me with this? Well, look at the molar mass. Oxygen is, atomic mass is 16, correct? Multiplied by 2 is 32. 32 gram per mole. How about nitrogen is 14, atomic mass. Molar mass is 28. So it looks like the smaller the gas, the easier it will go diffuse, it will go through. Are you following me here? The smaller the gas, the smaller the molar mass of a gas, the easy that gas will penetrate through the small tiny hole or orifice or whatever. So that's called Graham's law. And it makes a big sense. So if you have a large gas, large molar mass of a gas, that gas with the big molar mass will not go through. You'll stay behind for a while because it's just the molar mass. It's not supporting the size of the hole. The hole is small. So the smaller the gas with the molar mass will go through. So like hydrogen, it will be just as 2 gram per mole. 2 hydrogens, 2 gram per mole. So it will be the fastest to go through any orifice or any hole you can. So you can see this. This is, I wanted to write this one here in your for exam number 4, the last exam. I have it ready, but I will I have to wait until closing it until the end of we are coming after Thanksgiving, because if I open it now, some people will jump in, then we'll start taking the class, the whole thing. It's 30 questions this time because 3 chapters. Then jumping in too fast will have consequences in terms of bad grade. So therefore, I'm just avoiding to post it now because somebody will rush to do it, and then that somebody will affect his or her grade, because it's not good to jump into before you are doing all the online hour first. Are you following me here? So you have to do first the hour, and to do this time, I make for you very good exam, homemade one, and therefore I have to see that you are ready for the final exam. You are ready for the final exam. So this is the formula you have. The rate of a gas A divided by the rate of the gas B equal to the molar mass, correct, of B is the indirect proportional. See here? Let me take this one here. So if this is B, so its molar mass is here. This is A, smaller mass is here. So there are indirect proportions. Determine which gas is faster than the other, which one will go through the orifice or through the hole faster, or penetrate through the hole faster. So let's look at one of the examples here. Let's look at this. It says, at the same temperature, which molecule will travel fast? Oxygen or nitrogen? How much faster? So just without calculation, which one we say? Which one? Oxygen is 32 grams per mole, and nitrogen is 28 grams per mole. Which has the least? Nitrogen, correct? So nitrogen will go through first, faster. But how much faster? So you have to do calculation. And the calculation here is in the second. So lower molar mass, as we said, that's always the case. Always the case. The fusion means going through small tiny orifice or hole, and the gas will lower molar mass will go first and faster. So how much faster is? So you put the formula here. The top you put here in the top is the molar mass of oxygen, correct? So here it is, whatever is molar mass of B. Let's put this one here. Molar mass of B is 32, correct? Gram per mole. And for the gas this is for oxygen, correct? And for this is 28, correct? 28 grams per mole. And can take the E out for the units here. So, and this one here will be your, because this is 8, remember this cross, this is nitrogen. Oops. This is nitrogen here. And this one here is oxygen. So you do your calculation, and you can see the answer is here is nitrogen has lower, and you put this, the whole thing is 1.7 times faster, right? So you can put this one here. So let's put the second one. At room temperature, xenon atoms have an average speed of this. At the same time, at the same temperature, what is the speed of hydrogen molecules? Well, you know which one will be faster, the xenon or the hydrogen? But the xenon atomic. How much is it, guys? How much is xenon atomic mass? 240. How much is it? Come on, guys, can you read it? Xenon XE is there. So how much? Well, if you don't, then I have for you the hold on. I have the B table here somewhere. 100. Okay. Okay, so you have 100, 139, 131. Okay, so here it is. This is hydrogen, correct? And this is hydrogen. This is the speed of xenon. So the xenon atomic mass is this one here, correct? And hydrogen is 2. So you can determine the rate of hydrogen. And believe it or not, hydrogen is a smaller one, smaller gas. So it will have a higher speed. So it will go through very, very fast. See how much fast? Between 240, you can divide this value here by 240. You can see it. It's almost more than almost 9 times or 8 times faster than the xenon, correct? So, and the third question here is the same. What is the molar mass of a gas if it diffuses 0.1907 times the speed of argon? Well, you don't know what the molar of this gas, but we know the formula, correct? So you put the formula here instead of the gas here. You can look at this. Take this one here, and you have molar mass. You don't know, correct? So I'll put this one here. I don't know what's the molar mass of this. So here it is. I'll put this one as molar mass. I don't know. Then we have argon, correct? Argon, how much is the atomic mass of it? Is what? Argon. Somebody will tell me. 39.95 gram mole. And this is argon, because that's cross here. That cross argon, correct? And this is, take nitrogen out, this is argon here. And the other one is faster, which is the molar mass of the, this is the unknown here. This is the unknown gas. And this molar mass of okay, so cross multiply, and this one here, the argon is given to you. Argon is 0.97, so it will be, here it is, where we did this one here. Here it is. Will be, rate is 1 over, correct? 1 over, this is 1. This one will be of argon is, you can put it just 1. And this one here is faster, 0.907. Then cross multiply, you just square those square both sides. Take the square roots of to get the molar mass, and here it is. The answer is here. This one here, 1 over this, x over the molar mass of argon. So you can tell this is the molar mass of 48.5 gram per mole. So we'll come to the last topic here. And the last topic is, what is ideal gas? There is no ideal gas. That's a theoretical invention of our own. So real gas can behave ideally, yes. Those are ideal, those real gases at the temperature like at the sun, like methane. Methane found in the sun, hydrogen found in the sun. Some gases found in the earth, they are found in the sun as well. So those gases at the sun temperature and very, very low pressure, they behave ideally. So you can see a real gas can behave ideally at the sun temperature, so at very temperature. So this is what's a real gas. Now, ideal gas, there is none. There's no ideal gas as we see. So meaning if you have an ideal gas, is this ideal gas, when you freeze it, there's absolute zero. So there is no connection between the atoms, correct? Each atom by itself. So for this ideal gas. However, the real gas, when you freeze it at 0 degree absolute temperature, minus 273 Kelvin, guess what? They come together. They come together and they will start having some interaction among themselves. So therefore, you'll see interaction between, if there's frozen, like a frozen gas, a real gas, when you freeze it at absolute zero, you will see those molecules will come together. But ideal gas, they don't. They spread out all over the places. So therefore, there is no ideal gas. It's just we use it to help us to calculate the conditions we have. Correct? So I think that's That's all for whole chapters. And I will go now for the stop recording here.